Welcome to The Explainer. Today, we're taking a fresh, expanded look at a classic geological concept. We are going to trace the rock cycle from deep within the Earth's churning mantle all the way out to the very edges of our solar system. Let's dive right in by asking a seemingly simple question. Is the ground beneath your feet truly permanent? I mean, it certainly feels that way when you're standing on a massive granite mountain or walking across a desert valley. But that permanence? It's a complete illusion. What you're actually standing on is a massive, churning, recycling facility that operates over millions and millions of years. These rocks don't just sit there in equilibrium. They are constantly changing and adapting as they encounter new environments. Section 1. The illusion of permanence. The three rock types. So let's start with igneous rock. But rather than just thinking of this as, cooled magma, I want you to consider it the raw, reset material of the Earth's interior. When rocks are pushed deep enough under the Earth's surface, any of the main types will ultimately melt right back down into this raw, liquid state. And then, once conditions change that magma can no longer stay liquid, it cools, it solidifies, and boom, the cycle restarts. Now, what's really fascinating here is the stark contrast in exactly how this molten rock solidifies. You've got intrusive, or plutonic rock, which cools very, very slowly deep inside the Earth. This slow burn gives crystals the time they need to grow, producing a really coarse-grained texture. Think of granite. On the flip side, extrusive, or volcanic rock, erupts right to the surface as lava and cools incredibly fast in the atmosphere. This rapid cooling creates fine-grained rocks like basalt. Or, if it cools so fast that absolutely no crystals form at all, you get a natural glass, like obsidian. Moving on, we have a sedimentary rock. Once they're exposed to the atmosphere, rocks are actually quite unstable and highly subject to weathering and erosion. The elements break those original rocks down into tiny fragments that accumulate, get buried, and fuse together over time. This is an active process called lithification. And this category is just incredibly diverse. We're talking everything from fused sand and clastic fragments to precipitate rocks formed from dissolved chemicals, and even biogenic rocks made entirely from the accumulated fossils of living organisms. Crazy, right? Finally, we hit metamorphic rock. When pre-existing stones are subjected to massive compressional forces, like during mountain building, or baked by an intruding pocket of hot magma, their physical and chemical structures are fundamentally altered. But here's the kicker. This happens without them ever fully melting. This intense, high-pressure environment reorganizes the minerals entirely, often creating those really distinct, beautiful bands of color we call foliation. Section 2. The tectonic engine, driving the recycling plant. Now, this whole recycling engine builds through what's known as the Wilson cycle, outlining the opening and closing of ocean basins. It kicks off at divergent boundaries, or spreading ridges, where new magma upwells to form juvenile basaltic ocean crust. As tectonic plates pull apart, this brand new rock is carried outward. Eventually, this crust slams into a subduction zone and is literally dragged deep underground, right back into the mantle. Down there, the immense pressure and heat restructure the rock, driving off volatile materials like water, which actually melts the wedge of rock right above it. This buoyant magma then rises back up and erupts to the surface as island arc volcanism. The cycle ultimately closes when continents crash together. Because silicic rock is just too low in density to be subducted, the continents simply crumple. The rocks are folded and faulted into massive mountain ranges, creating intense regional metamorphism deep inside. But at the exact same time, this collision subjects those new high peaks to accelerated erosion. They're worn down, dumping giant piles of sediment straight into adjoining ocean basins, which feeds the creation of massive new sedimentary rock layers. It's a perfect loop. Section 3. The power of water, the ultimate catalyst. But listen, tectonics isn't working alone to power this engine. Water is the ultimate catalyst here. On the surface, it dissolves minerals and mechanically breaks down rocks. Deep underwater, circulating seawater interacts with fractures in new basaltic rock, causing hydrothermal alteration, processes like serpentinization, which actively weakens the oceanic crust. And crucially, water released from that sinking tectonic slab in a subduction zone actually lowers the melting temperature of the overlying mantle. That's what promotes the partial melting that feeds our volcanoes. This perfectly illustrates the immense interconnectedness of our planet's systems. For instance, when marine limestone, which is a sedimentary rock packed with carbon, is dragged down into a subduction zone, it releases carbon dioxide. This directly links the rock cycle to the global deep carbon cycle. So the movement of rocks is actually sustaining our biosphere, locking away and releasing carbon to help regulate the atmospheric conditions that are absolutely necessary for life. Section 4, the cosmic rock cycle, shattering geological geocentrism. Now, I want you to consider this staggering number, 52 million kilograms. Earth is an open system, constantly exchanging material with the cosmos. And that number, that represents the amount of interplanetary dust our planet receives every single year. And during the early stages of planetary evolution, this influx was even more massive. So our terrestrial rock cycle is, and always has been, continuously incorporating extraterrestrial material. So, where does this cosmic rock cycle actually begin? Well, it starts with the explosive death of stars. Stellar winds and supernovas produce interstellar dust, including pre-solar grains. We're talking microscopic crystals of diamond and graphite that are literally older than our sun. These grains enter protoplanetary disks, where turbulence and heat vaporize and remelt the material into tiny objects called chondrules. Eventually, these free-floating rocks clump together to form primitive asteroids, acting as the raw building blocks for brand new planets. And rock cycles are churning across the solar system right now, driven by forces we don't even see on Earth. On asteroids like Bennu, liquid water once circulated inside, transforming silicates into clays through aqueous alteration. On Jupiter's moon Io, intense gravitational friction causes tidal heating, which melts rock and drives violent, continuous volcanism. On Saturn's Titan, you've got a methane-based cycle actively eroding the landscape right alongside cryotectonics reshaping icy surfaces. And even on airless bodies like Mercury and our own moon, we see planetary-scale tectonic deformation driven simply by the rocky interior shrinking and cracking as it cools down. Plus, even without an atmosphere, rain, or wind, rocks in space are constantly breaking down. Airless bodies experience a relentless form of erosion called space weathering. Constant exposure to high-energy cosmic rays, irradiation from solar wind, and just endless bombardment by micrometeoroids chemically and physically alters their rocky surfaces over time. It's a completely different kind of erosion, but it's happening constantly. We know that hypervelocity meteorite impacts can generate enough force to eject terrestrial material straight out into the vastness of the universe. Those fragments travel through space and are eventually captured by the gravity of other worlds, entering completely alien rock cycles. Knowing this, we really have to ask ourselves, are the rocks in your own backyard destined to one day travel the stars? The rock cycle isn't just the story of the ground beneath our feet. It is the physical heartbeat of the entire universe. Thanks for joining me on this explainer. Keep wondering, keep learning, and I'll see you next time.